Hello everyone. So today we are from group 1 going to present our mini project of ICD. So for this mini project we have to evaluate the complete IC design of CMOS using mantographies. So this is our Boolean equation. Z equals to A plus B times with C bar plus D. So using this, we construct the transistor level schematic CMOS design. So for this CMOS design, there will be pull-up network and pull-down network. Number of transistors we require is 12. Each gates of A, B, C, D consists of two transistors where C bar is inverted. When it is inverted, it consists of another two transistors because CMOS consists PMOS and NMOS. So since our equation doesn't have any longer bar, we have to put inverter at the output. So the output Z will be consist of two transistors, which is NMOS and PMOS. The total transistors will be 12. Using mantographies, we are able to design this transistor level schematic. For example, to explain full about this schematic, transistor level schematic, I will give you an example. For PMOS, A and B connection, if A and B, the connection will be parallel. If A or B, the connection will be series. So for NMOS, it will be vice versa. I hope you understand. So the further part, my other team members will be continue. Thank you.
As I show here, the testbench circuit that was created before we run the simulation to generate the output waveform. So basically, the testbench can be as simple as a file we clock at the input header, or it could be more complicated, which include files that has error checking, files input and outputs, and also conditional testing. Conditional testing is just a tester that you have run before. You can move on the another stage. Okay, so the one on the right is the generator output waveform that we can obtain the running simulation. However, on the left is the truth table we obtain from the Boolean equation. So this truth table and output waveform for relates on another. So we can use the truth table as a way to verify the output waveform obtained after running the simulation. As convey the same information as the one in the truth table. Okay, in the order to verify if the input and output conveys the correct information, we first have to look the truth table. So if the input A, B, C bar and D is 0, 0, 0, 0, 0, the output Z should be 0. So as shown on the waveform, for the sake of saving time, we can use this information as I've listed down all on the waveform. We can use it as a way to verify if the input and output generated in the waveform conveys the same information for both inputs and output as shown in the truth table.
Hi, my name is Dinakar. I am from Group 1 and I will be talking about the Euler path. The Euler path is the path that connects the graph around all the vertices and all the path that travels around all the edges of the graph. And it has to be traveled around only once. The path should be chosen where each transistor goes across, like the path goes across each of the transistor. The Euler path is important because it is used to minimize the size of the layout. In this way, we can construct an efficient layout. There are certain rules when it comes to constructing a Euler path. The path should be defined by the order of the name of the transistor name for each of the input. The name of the inputs can be alphabetical like A, B, C, D, or it could be D, B, C, A, or it can also be 1, 2, 3, 4, or anything. As you see, it is also important to construct in such a way that there is only one variation for the pull up network and the pull down network. For group 1's Boolean expression, we chose to start from C bar. Hence, it goes by C bar, D, A, and D. Thank you.
Good morning. My name is Kishore Kumar Gunasekharan, metric number 211031377, and course from electronics engineering. So for our mini project for IC design, so I'm going to explain about the stick diagram today. This is our stick diagram for our layout for this mini project. Before we enter to the stick diagram, we need to know these stick diagrams are the basic guideline for our transistor layout. First, for the PMOS part, our VDD connected, and then for NMOS part, our grounding is being connected. So from the top part of the stick diagram is VDD, then the bottom part is ground. So first of all, this is the part is dotted was the N well, then the lower part is P well. All our polymers are connected based on our previous schematic diagram, and then all our connections are based on the Euler part. That's all. Thank you.
Hello everyone, my name is Sasikan Analaki Bhaskaran. I want to talk about layout design. This is our final layout design, and this layout is manually do in Mentographic software. So this is no DRC and LVS error. For the DRC design rule check, have few requirements. For the diffuser region, with 3 lambda for the active layer and 3 lambda for spacing. For polysilicon layers, with 3 lambda, and the spacing between 2 poly is 3 lambda. Metal interconnection layer used to form the VDD ground and output. For the contact layer is form interlayer connection. It is our final output for the DRC. There is no error in this. After the DRC, we must do the LVS, layout versus schematic. During the LVS, we occur some errors while doing the LVS. Example of common errors in LVS is missing port in polysilicon. So we tried to overcome the errors. The solution for the errors is the label of input as an example ABC must be within the poly. F other solution for the errors in LVS, which are make sure the wires are no overlapping. P well and L well contact must be placed on VDD and ground respectively. P plus and N plus is compulsory to construct in N well and P well. For layout, make sure the N well and P well is same as the network circuit. Okay, this is our final output for the LVS. When the LVS is no error, it's got the tick mark and smiley emoji. Okay, that's all from me. Thank you.